Okay, well, actually, the room's quieted down. We're a couple minutes after the hour. So hi, I'm Jake Slutsky. I'm just going to be emceeing for the next 90 minutes. I'm going to try and keep us to time because I have a poster to present upstairs. So without further ado, our first talk is from Lea Bischof. Please go ahead.
All right. Yeah, thanks. I hope you can hear me well. Welcome to my talk. I'm Lea Bischof from the AI in Hanover, and I'm talking today about optical verification of the laser phase detection system. So what I'm talking about is the SDPC, an acronym that you heard about a lot this week already. It stands for Signal Detection and Processing Chain. Especially yesterday, there was a talk by Ada Ominska about interferometry testing, where she gave a nice overview about the SDPC and also already gave a teaser about the talk and the measurements I'm presenting today. As a little reminder, the SDPC starts at the quadrant photoreceivers in laser. So in our 3 interferometers, we have 2 quadrant photoreceivers in the test mask, 2 in the ref and 4 in the science interferometer. Their signal is then going into the IPU, which is a interferometric processing unit, where we have the BEEs, the back-end electronics, and they are matched for the different QPRs into different power levels of their respective interferometers. The next part is the PCU, the phase meter control unit, which eventually outputs our data and also gives the signal towards the local laser for the frequency control of the transponder lock and the phase modulation for the PRN sideband and inter-spacecraft link modulations. And then finally, we have all the cables connecting these different units, and this is what we call the harness. And this whole chain that I just described is what we call the SDPC chain. It has several tasks, and I want to present the ones that we are interested in testing. So the first one is the signal detection and processing of the data, and this refers to the phase readout of our 3 interferometers per optical bench. Another important part is the clock distribution, which is happening via the sideband modulation and the PRN ranging and interspacecraft link that are also happening with the phase modulation. The other part is the frequency control, which is done by the SDPC, which is about the transponder lock between the lasers and the beat node acquisition. So another very simplified sketch of the SDPC shown here in the top. We have our 8 quadrant photoreceivers, our IPU, our PCU, and the harness in between. And the input in the SDPC is an optical heterodyne beat node signal. And one of the very important outputs is the phase readout, which we have to show has a certain performance within our laser requirements. So I want to talk about the optical verification that we want to plan for the SDPC. So we really want to have an optical input and test the phase performance at the end of the SDPC. And this test is planned to be performed with EM level components, so EM models for each of the units, and optical signals as input. I've been highlighting that the phase readout is one of the big things, and this is because this is one of the big things that are really hard to measure, because you need to have a very good reference, or a reference that is as good as your requirement, to show that you're at the requirement. Or what you can do is a so-called 3-signal test, and this is what we are doing with optical 3 signals. And that's what I want to present to you now. We have this experiment that we call the hexagon experiment, and we see a schematic on the left side. So we have 3 laser beams as an input, the green, the blue, and the red one, and they are combined in this hexagonal interferometer in the center of it, where all the beams are combined pairwise so that we get 3 output beat nodes. So 3 beat node signal as pairwise combination from the 3 input lasers. And in order to visualize this a bit more, I've shown you here a frequency axis, just very simplified, showing we have again our 3 different colored lasers at 3 different frequencies. And you can just see from this graphic that if you add them up with the corresponding signs, they will cancel to 0. And this is equivalent to saying, okay, the phases that we measure for the beat nodes of each of the interferences, they add to a constant value. And now the idea is that we send these phases into our SDPC, and at the end of it, it still needs to add up to a constant value. And this is the idea of a 3D signal test, and this is how we generate an optical 3D signal test in this experiment that we call the hexagon. So I'm going to show you a picture of this beautiful optical bench that is forming, or that is the hexagon interferometer. It was built at the AI in Hanover by some of my colleagues. It is quasi-monolithic, so it's a piece of glass. It is bonded with UV curable glue, and it has optical parameters of more than 96% heterodyne efficiency in each interferometer and very equal beam parameters between the 3 input beams. So it's just very nicely done. And the idea is now we take this optical bench, put it in the center here of the picture. We have a laser GSE that is providing the 3 different input beams that are sent into our hexagon interferometer. We have the QPRs that read out all the 6 outputs of the interferometers, and the signal is processed by the IPU and PCU. We get our output, and we also control the laser system with the phase meter. So the very first thing we did was building this whole setup with GSE components. Because, of course, we don't have the EM components yet, and because we have to verify that our optical signal generation is good enough to perform these tests within the LISA requirements. And this is a result that I'm showing you here. So I'm showing you an amplitude spectral density. You can see the three high lines are the phase readout of the single channels, and then combined to such a 3 signal combination is a thick violet line in the bottom. And I plotted as a comparison a 1.3 picometer equivalent to show you that we indeed reach a very low noise level, which shows that we can actually create optical signals that will enable us to test the STPC with the hexagon interferometer. So at this point, I want to point to a publication from some of my colleagues, Daniel Penkart, Pablo Martinez-Cano, Yong-Ho Lee, and Miguel Duvala Alvarez, who have written a paper that's currently under review that very nicely describes the design, construction, and preparation of the facilities in order to make the measurements that I'm presenting here. So one important goal with our hexagon measurements is that we want to verify our LISA model with it. So we have a model that is describing the performance that we expect for the STPC. And our plan is for the hexagon measurements to design them in a way that the results of the measurements can be compared to the predictions of the model, and then thus enable us to do a model verification. Okay, but what are we actually testing? We're testing against STPC requirements, which are requirements flown down from the LISA high-level requirements. And we apply certain ones that we can only test in hexagon that we need to test with hexagon. And they include interface testing, like between the QPR and IPU. When we connect it, we need to make sure the signal is clean, etc. Then a very big part are the functional and performance tests. And here I'm just giving you 2 examples. So we want to make sure that we verify the phase readout performance under weak light conditions. So in the science interferometer, where we have this very weak light beam, there we need to verify the phase performance. Another example is the acquisition sequence that we also want to test in our measurements here. The next big step is the sensitivity tests. And what I mean here is that, for example, we do again this phase readout performance under weak light test, but we add a temperature ramp to it. And then we see how the system reacts and how the phase readout changes with temperature. And finally, we are going to do some electromagnetic compatibility tests. Okay, so there are some differences between LISA STPC and what we see in hexagon, which is just by design, because the hexagon was designed for this 3 signal test that I mentioned earlier. And therefore, we have this symmetric design of the 3 interferometers that combine the different beat nodes pairwise. So we don't get 3 interferometers that completely resemble the LISA interferometers. And in order to use this for testing, the logic that we are doing is we're saying, okay, we are looking at one LISA interferometer at a time and tune the parameters to be representative for this specific interferometer. test the STPC readout for these parameters, and then go on to the next one. So here I'm just showing as an example the science interferometer. So we can say the interferometer on the right side we pick to be a science representative between the power levels of the two beams there accordingly. And then we have the blue okay, and then we have the blue beam that we can still decide how to tune the power. And for example, you can also tune it in a way to get a second interferometer that is representative for the science IFO, or we could tune it in a different way if that makes more sense for the test case. So one of the examples I've mentioning earlier is acquisition. So this would be basically the setup. We have in our laser GSE one laser that is controlled by the PCU, while the other two lasers are controlled by the GSE PMS. We have one interferometer inside the hexagon that we tune to be the science interferometer, and then we perform the acquisition sequence, and the output of this measurement is the verification of the B-node acquisition process. This is just again the picture of how we might tune the power levels for this specific case in order to represent the science interferometer. And the idea is for the acquisition sequence, we have to go through different parameters. So we have to test it in the whole heterodyne bandwidth. It doesn't have any modulation because that's not needed during the acquisition sequence. And normally we have certain heterodyne efficiencies that we would expect during acquisition. But because the whole optical bench is built quasi-monolithic, we cannot adjust the heterodyne efficiency. Thus, it means we have to take care of this or keep this in mind when we compare this to our model. The other performance measurement I've been mentioning is the weak light case. It's basically the same setup, but we want to focus now on having the transponder log working, having all the modulations applied, and we are looking at the phase performance readout for this case where we have the weak light condition in the science interferometer. So again, we tune the power levels, we look at different frequencies to verify this, we have all the modulations applied, and verify the performance at the weak light case. So these are the facilities that we are using to do these tests. So in the center, you see a picture of the whole lab. On the right side, you see a zoomed in picture of the laser preparation. So we have all the commercial components that prepare the 3 lasers that will be sent in the system. They are via fibers connected to the optical vacuum chamber. On the top, you see a zoomed in picture of that one. It houses the beautiful optical bands of the hexagon within the thermal shield, like several layers of thermal shielding surrounded by currently GSE QPRs. And now the signal of these QPRs are sent to the next vacuum chamber, which will house the IPU and the PCU. And so this is this big chamber you see in the center, which is a thermal vacuum chamber, which can really ramp the temperatures to all kind of ways you might want to use to change the temperature of the IPU and PCU on. And it's important that this is separated from our optical bench because the hexagon interferometer was built to be a laboratory experiment, not to go to space. So it's not meant to deal with really high temperature changes. So it cannot be in the same vacuum chamber as the 2 phase meter parts that we are testing in there. And again, just a little reference to the paper that is describing this very nicely. And that already brings me to the end of my talk. So I've been showing you that we are planning on verifying key functions of the STPC at the AI by using optical signals as inputs. We have shown that our optical signal generation are sufficiently stable for this, and we are currently in the process of setting up and calibrating the testing facilities. The test cases will, as a key part, have the functional and performance tests and sensitivity tests, and these tests are scheduled to start 2027, which is next year. So with that, thank you.
Thank you. Okay, so we do have a minute for questions, if anyone has something. And I didn't see any online yet. I had one on one of your early plots. Actually, you're showing it on this in the top right. The noise plot. So that red curve, that's the noise floor of your test bed in some kind of test?
Like the low one? So that's this 3 signal combination.
Right. So it kind of kisses the requirement that people might want to verify on it. So it's there. So I'm curious, how well do you understand the noises in there from the perspective of verification, just so people could be confident that a measurement might actually be below?
So actually, I purposely called it an equivalent, not a requirement. So more plotted here so that people have a reference. We actually have newer measurements that are even below that. So yeah, maybe that already makes some people happy.
Sure.
So I think this is actually the Moku phase meter limiting this.
Great. Do we have any other questions? Okay, going once, going twice. All right, thank you, Lea. Oh, let's get Catia set up.
Thanks.
Yeah.
Hi.
And okay, Catia, you have 12 minutes. Please go ahead as soon as you can share. Looks good.
Okay, great. In this presentation, I will focus on some areas of investigations related to the space weather field that will be carried out with LISA. For those that are not very familiar with space weather, I recall that basically refers to the variable conditions in the inner heliosphere due to the solar activity and major astrophysical phenomena. As Valeria recalled in her talk, space weather and cosmic ray physics are part of the complementary science in the LISA science team for LISA. Let me recall that also that LISA is a natural multi-spacecraft observatory that will carry identical particle detectors, will measure hydrogen and helium above 70 MeV per nucleon and below 400 MeV per nucleon, and will carry also magnetometers. With these two diagnostics, these two kind of diagnostics instruments, we will be able to monitor some of the interplanetary medium parameters, and others we will monitor through machine learning models that we developed on the basis of the experience we gained with LISA Pathfinder. So the interplanetary medium consists of neutral hydrogen and a continuous flow of plasma. This is neutral, but is also charged. It is a charge quasi-neutral that expands from the sun, and since LISA will be on the ecliptic, basically we will see continuously the slow solar wind that comes from the equatorial regions of the sun with speeds that lie in the range of 400 kilometers per second. On top of it, we will have high-speed solar wind streams from coronal holes that will push on this slow wind that also drags the interplanetary, the solar magnetic field in the interplanetary medium. In addition to this, we will have other structures that I will illustrate soon, and also particles and high-energy particles of galactic and solar origin. Particles and fluctuations in the electron-dense interplanetary medium are the most impacting factors on LISA. So the sun undergoes an 11-year solar cycle, quasi 11-year solar cycle, a large number of sunspots that is the most widely used proxy used to indicate the solar activity. When you have a high number, you have the solar maximum. When you have no sunspots or very few, then you have the solar minimum. And this is exactly a solar minimum when you have the maximum flux of galactic cosmic rays, when you have not so many at solar maximum, but it's when you have a lot of solar particles, when you have a lot of interplanetary structures. Saying that we were gaining experience with LISA Pathfinder, the reason was the LISA Pathfinder was in L1 at the distance where we're also orbiting distance short enough from the point of view of the interplanetary medium parameters, where also ACE and WIND, the NASA missions that are devoted to the monitoring interplanetary medium. So we could use those data in addition to the LISA Pathfinder data to understand what we were observing. And this, this experience can be applied to LISA. So while LISA Pathfinder was in orbit during the declining phase of the solar cycle 24 with a low to medium to low solar activity, then LISA should be in a space starting at the maximum. With the solar cycle, it should be very similar to the present one. If this won't be the case, we will know it in a couple of years. I don't have time to explain why. But this is it. In addition to the slow and fast wind, we have this emission of huge billions of tons of coronal mass that produce this shocks that accelerate particles. You see this snowstorm effect on the C3 coronagraph on board Soho. And in addition to the major acceleration of solar particles that go through your spacecraft, these structures also have an impact when go through the three LISA spacecraft, an impact that is different on the three spacecraft and different on the laser links. The other huge structures that are in the interplanetary medium are the heliospheric array sheet. We had the talk by Daniel Serrano that reported about possible connection between glitches and heliospheric array sheet crossing. We are talking about this thin layer of current that separates the two polarities of the global solar magnetic field that expands in the interplanetary medium. Actually, what happened when you go through these structures depends very much about what happened before. It means that if you go at solar minimum, solar maximum is a different condition for the heliospheric array sheets. If another structure just passed before the spacecraft, like an ICME or an ISP stream, the conditions change completely, the dimension change completely. So you can have a small magnetic field or a high magnetic field, even under similar conditions of the solar wind speed. But what you always certainly have is a major increase of the noise associated with the variations of the electron density along the laser beams. So going to the particles, we studied short and long-term variations during the time LISA Pathfinder remained in orbit. You see the increasing trend of the galactic cosmic ray variations was associated with a decreasing solar activity, while the spikes are associated with the passage of the interplanetary structures, high-speed solar wind streams, and ICMEs. We observed 45 recurrent depressions, larger than 2 days of the galactic cosmic ray flux. This is due to the passage of high-speed streams. We will see hundreds with LISA on the three LISA spacecraft, and we will see tens to 100 ICMEs, and the effect of the heliospheric array sheet, both when they will be isolated or when they will be they will occur together with the passage of the other structures. I give you an example. This decrease of the galactic cosmic ray flux on July 20, 2016, observed with LISA Pathfinder, was due to the coincidence of three different effects: the passage of an high-speed stream, the passage of an ICME, and an heliospheric array sheet crossing. So we will have the chance to study the energy dependence of the galactic cosmic ray variations under all these possible mixed occurrences. Talking about magnetometers, we were able to retrieve from the platform magnetometers on board LISA Pathfinder the passage of the ICMEs. These are two ICMEs, and these are LISA Pathfinder data. And we compare our magnetic field observations with those by wind. We got a very nice agreement. So we will have the chance to study also when these kind of structures go through your spacecraft, both effects on the magnetic field and on the electron density that will recover through different sets of machine learning models that we have developed with LISA Pathfinder. The two sets of models allow to infer from galactic cosmic ray variations and magnetic field measurements the solar wind speed that won't be measured on board LISA. So we will discriminate between the passage of high-speed streams and ICMEs because this trend of the data or the inferred data is not feasible. We will also estimate the electron density fluctuations in the three LISA spacecraft, and we will try to retrieve the average variations along the laser beams. Both sets of models have been have been considered just with, not just as a black box models, but also with knowledge extraction to verify what we obtain actually as a meaning from the point of view of the correlations of all the plasma parameters. Galactic cosmic rays, this is what we expect at the beginning of the mission, so a low flux of galactic cosmic rays, a higher flux at the end of the mission. This is comparison with LISA Pathfinder. The radiation monitors will measure data up to here, but we may extend the observations with models above this energy. Analogously, we will measure variations, short-term variations due to the passage of high-speed streams and ICME. With respect to major events in terms of solar energetic particle events, we studied in detail the occurrence of SEPs during this solar cycle with solar orbiter. What we have found is the maximum duration of one single event is 5 days. The average duration is 1.5 days, and Valerio in his talk reported on the charging of the test masses during an SEP, was this SEP that was monitored with the EPD hat on board solar orbiter. The fluxes of these particles are very different from those of galactic cosmic rays, so they also have a different impact on the charging of the test masses. But since the flux goes up in minimum times on 20 minutes, so up to 5-6 orders of magnitude, it can happen. We observed with solar orbiter an extremely intense event. It was observed only with solar orbiter because it was on the other side of the, of the sun with respect to Earth. So this was not observed by near Earth observatories, and it was so extreme, let's say, that one event like that one happens once every 10 to 15 years. So this is basically my last slide before conclusions. Another possibility to see at the same time a huge increase of the test mass charging and of the energy released in the particle detectors may be associated with strong, very strong, long and short gamma ray bursts. If that acquisition on the radiation monitors will be of the order of 4 seconds, we might reconstruct the direction from which the photons were coming, and this may be very interesting for the mission. You never know. You observe also a gravitational wave. So I conclude from the point of view of the contribution that LISA may give to space weather and to the heliospheric physics communities. We have the study of the energy dependence of long and short-term variations of galactic cosmic rays below 400 MeV per nucleon, the monitoring of the passage of all kinds of interplanetary structures by adding to the particle detector and the magnetometer measurements the artificial intelligence models. We will monitor the evolution SEP events as small steps in longitude with identical instruments. It will be the first time that this kind of measurement will be carried out ever. And the possible observation of short and long gamma ray bursts, and finally the possibility to improve our machine learning models with a much longer, sample of data. So thank you very much.
Okay. Are there any questions in the room or online? So there's a lot of information. I'm trying to make sure I caught it all. So it sounded like for the really big events that might actually trigger a safe mode or at least seriously degraded noise for LISA, you're saying there's of order 1 you'd expect maybe during the mission? Is that close to right?
Yeah, the number of, there are different kind of, worst case events. Let's say from relatively worst case events, we have the ICMEs, and the number changes very much from solar minimum, solar maximum. So we will have, let's say, 10 per year at solar maximum, and then the number will decrease toward the solar minimum, and the same will happen for SEPs. This is basically the same number that it is related to the, to the test mass charging. We studied test mass charging for many years, and I'm certain that the discharging of the test mass will be optimized under any possible condition, because it's most widely studied by us, but also by our colleagues at Imperial College. Trento is the most widely studied problem, I think, related to the interplanetary medium on LISA.
Okay. Anyone found more questions? Yeah, here's one.
Yeah, thank you for the talk, Catia. Could you explain why you decided to go for a machine learning model instead of more traditional approaches to reconstruct the quantity, the solar wind speed, and so on? Thank you.
Sure. The problem is that I didn't say that actually I had to do it. While LISA Pathfinder was in L1, so we had a bunch of missions that are devoted to control the solar-terrestrial relationship. LISA will be at 50 million kilometers from Earth, so we won't benefit of any other nearby mission to obtain this data. So we had to find a way to monitor, to fully monitor the interplanetary medium without hardware, basically. So this is the reason why, even if Vigil may be in space as the space weather mission by ESA, I'm not sure about the fact that the two missions will be in space at the same time. But in any case, it will be in L5, too far to use the data that they will get or they will be gathered near Earth. They are not usable for LISA, too far.
Okay, thank you very much.
Thank you.
I think we're going to move on to our next speaker. So that's Alvise Pizzella. Let's see.
Okay, perfect. Thank you. So first of all, thanks to the organizers for allowing me to present here. I really couldn't be there because my second child was born a few weeks ago. But yes, today we'll speak about the testbed, and I will start with curvature mismatch, for which I gathered these 3 examples here. It's not a very easy thing to exemplify. But if you put dishes in the dishwasher in a very tidy way, it works way better than if they are not, especially because of the curvature of the dishes, or flat Earth versus round Earth, or trying to eat from a jar with a spoon which has a different curvature than the jar itself. And this carries straight over also to interferometry, because when you interfere 2 beams, the beams have a curvature, so have a wavefront curvature, and the result depends on how they are matched to each other. So as an example here, I overlap 2 beams with slightly different wavefront curvature. The interference pattern to measure at the end depends on this relative curvature mismatch. In this case, it's very slight, but you can increase it by having a shift of 1 beam, or even more if we have a tilt of 1 beam, which is going to happen in LISA, indeed, because of the very well-known tilt length coupling, tilt of the spacecraft, tilt of the test mass. And when you try to measure interferometrically, what you do is you place a photodiode at some point, and then the only thing which matters for what I'm going to speak about today is what happens at the photodiode. And there, for instance, here, the wavefronts are perfectly in phase, and they would interfere perfectly. So I associate to this like an optimum power. If I take into consideration a point slightly above there is some phase offset, which leads to a decreased interference power, how to say. And when you try to, so when you collect all of this information together at the photodiode, which is basically averaging all of this, what you would get is, because of the different power at these 2 positions, some final value of phase, which is somewhere closer to the higher power one. So moving on, how do we bring this to an analytical framework? Well, this is exemplified here. It's in a publication which is currently in peer review. And so we only show tilts around the QPD center, because LISA will use imaging systems which make sure that tilts of the measuring beam always are centered there. And the only thing which matters is the waist and the radius of curvature of the 2 beams at the photodiode surface, which is what they call here WL and WM. And the resulting waist size and radius of curvature of these two beams can be mathematically collected with the formulas shown here. And a very good way to represent the relative radius of curvature mismatch is given by this parameter rho, which compares the beam spot size and the absolute radius of curvature mismatch. This parameter, by the way, is comfortably small, luckily, typically with typical LISA-like beam sizes, which allows also to expand around it. So mathematically, what you do is when you interfere two beams, you have to sum the electric field, and when you take the square modulus, you end up having three terms: the individual beam terms and the overlap one. And when you are measuring the power on a photodiode, what you actually do is you're averaging all of these three terms. So what we want to focus here is on the green one, which can be written this way, where I singled out the heterodyne efficiency, a parameter which also Lea mentioned before, which is between 0 and 1, with 1 being a perfect overlap between the two beams and 0 being, well, a disaster. You get no signal out of that. What we have at AEI to measure this, what happens here is that if you measure the heterodyne efficiency on a single element photodiode for two beams and for some values of this radius of curvature, rho, because of symmetry reasons, this is symmetric around 0 and there is no big surprise. But an effect which went unseen for a while is that when you measure this on a quadrant photodiode, as Lea is going to be doing, if you have no waveform curvature mismatch, then this also peaks nicely at 0 for each segment of the photodiode. But if there is some waveform curvature mismatch, this does not peak anymore at 0. Actually, it shifts to one side, and the other segments, and this was an example for segments B and D, but segments A and C actually see the same thing swapped for the same angle tilt. And this, of course, leads to a situation where in the presence of tilts, some segments perform worse than others. And this can be exemplified with this picture here, where you see that on the top left, in the case of identical beams, the waveforms are always matched. On the top right, in case of identical beams with a tilt, there is still symmetry between top and bottom in this picture. The same holds also on the bottom left, where you have different waveform curvature but no tilt. But in the last case, bottom right, with a tilt and with different waveform curvature, the top segments are more in phase between each other, which explains why they interfere better. They have a higher heterodyne efficiency. So we have a facility at AEI which is capable of measuring this. It's the so-called TDOPS experiment. I'm not going to read the acronym, but it's a simplified version of the LISA optical bench, the one on the bottom, with on top a simulator of LISA's beams, which provides a Gaussian beam and a flat top beam, which can also be tilted via these actuators, and we can simulate a broad range of tilts from plus minus 2 millirad, which is representative of LISA's extreme cases, so to say. And here you can see the flat beam profile, which is generated via this flat top beam generator, which is an apodized aperture, which yields this nicely flat in intensity and wavefront beam. So this effect which I mentioned, I have measured it. And you can see here that when you tilt the measurement beam on an interferometer, what you obtain is that the peak of both beams is on the segments, in this case left and right, has a shift. And we have also developed a model which tries to exactly explain what we measure. The model comes pretty close. We know we have a 7% uncertainty in the angle calibration. Still, this doesn't manage to explain the mismatch, but yeah, I guess we just have quite big errors on uncertainties on our parameter estimation. What I want to now finally speak about is how this couples into the QPD signals, because the reason why we use QPDs is because we want to measure differential wavefront sensing. You want to be able to reconstruct the angle of the beams, not only the path length, which is represented in this case by the longitudinal path length signal, or LPS. So on the bottom left, in a case of no waveform curvature mismatch, so this rho equals 0, there is actually nothing new to to mention. So you have an optimal interference, both in the case that you're measuring these beams on a single element photodiode or on a QPD. But if you have some waveform curvature mismatch, you have on one side the issue that the maximum heterodyne efficiency that you cannot achieve at no tilt decreases. But you also have an effect due to the fact that when you have a tilt, some segments decrease in signal amplitude, so the heterodyne efficiency, faster than the other one. So in the case of before, this left minus right, one side worsens faster. And this couples additional noise because the noise is going to be given basically by the inverse of the heterodyne efficiency. In Lisa's current design, a value of rho up to 0.47 is still allowed. And so, yeah, we would advocate, if possible, to not have too high value of this curvature mismatch parameter. A second case which has to be analyzed is the case of correlated noises, which are correlated among all of the segments. The previous case was for uncorrelated noises. And here there is a similar thing going on, but with a dependence on the sign of the operation which is taken in this combination of the phases. So which is sum for the LPS and which is difference for differential wavefront sensing. So the easiest case is differential wavefront sensing. So if a noise is correlated, when you're subtracting segments between them, this noise would go to zero. It would cancel out, which is exemplified by this value diverging to infinity, basically. And a similar case happens in the LPS signal on the bottom left, where this is supposed to cancel out in case we have a 90-degree phase offset between the segments. This cancellation also worsens in the presence of a wavefront curvature mismatch. Yeah. Last, we are currently also trying to measure this noise. And so here you can see the result of a measurement where we are having two interfering beams and we just tilt the measurement beam. We keep the reference beam stable on the orthogonal on the QPD. The noise must be distinguished into active and passive axis because if we tilt the beam only vertically, well, there's no horizontal tilt, we call that passive axis, and the vertical tilt axis is the active axis. Noise behaves differently exactly because of this correlation, which cancels out in the passive axis and does not in the active axis. Correlated noise, in our case, is mostly relative intensity noise. The behavior is different, and we do manage to also explain it with the model we have of noise versus angle. We managed to explain the uncorrelated noise. We still don't manage to explain exactly the correlated noise, for which, I mean, the value shown here is a fit, but we would be able to explain that noise only if the measured relative intensity noise was twice as much as what we have characterized in the experiment. So we are still working on trying to find out why we have this mismatch. And that's it. Thank you.
Okay, great. Thank you. Do we have some questions? I see one.
So does this setup only simulate like the tilt at the telescope level, or there are also other tilts that can I produce the same effect that you can test?
So how to say, the setup has two steering mirrors, and with these two steering mirrors, you can physically tilt the beam around any point around its propagation line. The target as of now is to simulate, yeah, let's say both test mass tilt or telescope tilts. At the end, the only thing you have to do is to tilt a beam around the center of the QPD. Other kind of tilts, I don't know what you're referring to.
He's shrugging.
Yeah.
So I'm not clear we have another. I haven't seen any other questions. Are there any online? No questions online. Well then, thank you. And Marina, Orta, Terre, please.
So hello everyone, my name is Marina, I'm a PhD student from University of Barcelona, and today I wanted to show some performance of the LISA radiation monitor and the impact not only on the mission but also beyond the LISA motivation. So first of all, some of you might wonder, why are we putting a particle detector in an antenna that wants to detect gravitational waves? And the main motivation is because of the test mass is getting charged. So we are in space, and in space we have a lot of stars that we've seen in previous presentations. But the thing that we are currently concerned is the background radiation. So because we have different background radiation, this radiation interacts with the spacecraft, and it creates secondary particles. And these secondary particles may interact with the spacecraft, and they create a net charge on the test mass. So now we have a cube, but it's charged, and we have forces applied to it. And as we have seen in other presentations, these forces induced in the test mass are the dominant factor in the limit of the sensitivity of LISA in the lower part of the frequencies. So yeah, this is an important thing. We have different backgrounds that we expect during the LISA mission. You have seen also in Katia's presentation. Here we are mainly worried about cosmic rays, which are isotropic, slow changing. And also solar energetic particle events, which are spurious, directional, and they are very fast changing. And they are orders of magnitude that are more intense than the cosmic rays. As you can see in the plot below, they are way larger fluxes than the cosmic rays. And in particular, we are mainly concerned about protons, and protons above 100 MeVs, because they are the ones that actually may charge the test mass. So the radiation monitor is something that looks like this. It consists of a telescopic stack of 20 by 20 millimeters of sensitive area, so it's quite a small thing. It consists of different layers of plastic scintillators for the sensitive part and silicon PMs for sensing. And we have in between these plastic scintillators, we have placed different tungsten absorbers to slow down high energy protons in order to be able to reconstruct the initial energy of these protons. And everything is shielded by copper to avoid detecting protons that will actually not induce a charging in the test mass. So it will work more or less as follows for the people that are not very used to this kind of detectors. So when a proton is energetic enough to traverse the shielding, it will pass at least with one or more plastic scintillators. These scintillators have the characteristic of transforming the energy that is deposited in this material, and they produce optical photons. So we have this translation of the energy that the protons deposit in the scintillators to optical photons, and in two of the sides of each scintillator we have placed silicon PMs which are photomultipliers in order to detect these optical photons. In addition, we have for the front-end electronics the beta ASIC, which is a space-qualified ASIC that processes and digitizes the silicon PM signal, and also an FPGA for the processing and the acquisition triggers. So we have this really small particle detector that works on its own and is able to measure the fast changes in the flux. With that, we will be able to have an estimation of the spectra, and eventually we will be able to beat off fake gravitational wave triggers. So that's a nice thing with a relatively small detector. So the first thing that we do with this design is simulate, and we have done several Monte Carlo simulations with GM4. And in this slide, I present the radiation monitor response under isotropic proton radiation at different energies. So with the setup that I showed you before, we see that the energy or the signal that is created in each scintillator depends on the initial energy of the protons. So what we can do is to classify, let's say, based on the signal of the four scintillators, classify events in different energy channels that we call. So in a way, you can see in the plot on the right, this is the response of these energy channels that we define based on the combination of signals in the scintillators. And you can see that these energy channels have a response that is integral, which means that we can detect protons starting at a very clear threshold of energy. So, and these energy thresholds are different for each energy channel. So this is the way that we know we can have some idea of the spectra of the incoming protons. So since the telemetry is very limited, we cannot store all the data, and the strategy that we will use is to store and classify every event that we record in one of each of these 5 energy channels. So in the end, the data output that we will have is a count rate. We have this small thing that counts all the time, and we will have different rates in different channels of these 5 energy channels. So knowing the acceptance curves and also knowing the detection counts that we have, we are evaluating the reconstruction capabilities of this setup. So we have worked with an algorithm in order to reconstruct the flux. We assume a model. We model it with different parameters, and we try to minimize the real counts that we are measuring and the modeled simulated counts that we have. So in order, so when we manage to minimize these parameters, we have seen that the reconstruction is quite good. In here, I show you 2 solar events that were measured by SOHO and also some cosmic ray background model, and we can reconstruct both of them very good. Since the cosmic rays have a lower flux, we need about 1 hour of counts to be able to have a proper reconstruction. But for solar events, only with 10 minutes of data, we are already able to reconstruct the flux very well. So also we have tested experimentally this detector. We have tested in a test beam. We went to 3 facilities in Vancouver. And we have tested in the setup that you can see in the left picture. So essentially we tested the protons in the direction along all the scintillator planes. So in a way that if the proton is energetic enough, we'll have signal in all of the 4 scintillators. Also you can see the front-end electronics, the evaluation board that we are using in the laboratory, which is have the same key components that we will use in the final version. So the results look more or less like this. You can see that the distributions of the signal that we have in a scintillator depend a lot on the incoming energy of the proton, which is a good sign, and because it's the strategy that we will follow to reconstruct. And also we have seen the response under these proton energies. In this plot on the right, I show the response for different coincidences because it's the strategy that we will use. And we have seen that as we start increasing the proton energy, the coincidences start to increase. So the first curve is the coincidence of only the first 2 scintillators. When we increase enough, we start having coincidence of the 3 first scintillators. And in the end, I have the coincidence, so I have signal in all of the 4 scintillators. And this adjusts quite well with the simulations that we have performed. Also, we not only use the experimental data to validate the simulations, but also we have used it to fine-tune the simulations. There are several parameters that we cannot adjust with enough precision in order to have a simulation that correctly maps the real behavior of the radiation monitor. So what we did, it was to match the simulations with experimental data, and afterwards we have artificial noise in order to be able to map the noise that is not initially taken into account in the simulations, like in the scintillator, in the silicon PM photodetectors, and in the electronics part. So we pass from the plot of the right to the plot of the left, in which you can see that these different distributions of different energies, even though they keep the same mean value, they are getting the same width. So this means that we are mapping now correctly the true noise and the true behavior of the radiation monitor, which is a very nice thing in order to be able to have a proper flux reconstruction. So we are also investigating and doing several things beyond LISA. And also we are trying to assess the direction reconstruction, especially during SEPs, because SEPs are directional. And we have several advantages with this, because from one part, as Catia said in her presentation, we will have proton flux measurements in a region in space that is not static. We will be alone, essentially. We are too far away from anything else. And also, we are measuring protons in an uncommon energy range, because usually the satellites that are dedicated to solar physics don't measure or don't have any resolution above a few hundreds MeVs. So this is an extra information that we will have, and it could be also interesting for helioscience. And in addition, we have 3 spacecraft, and we will have 1 radiation monitor in each spacecraft. And with the separation, we'll have different arrival times. In the end, we're separated about 8 seconds. And also, it could be that we have a slightly different orientation with this radiation monitor, and also we'll have magnetometer data. So everything combined, this would be able to give us a lot of extra information, and also for space weather-related research. And even beyond of that, we have seen that the response of the silicon PM channels within a single scintillator is position dependent. So we also did another test beam at CERN SPS. And what we did was to test only a single radiation monitor scintillator. We placed fiber trackers before and after this single scintillator, and we have mapped the response of every channel with the position of every track that we tested. In this case, we had this test performed with muons, which are minimum ionizing particles. And here I also put these color maps in which you can see we have 4 silicon PM channels. I put a red square in order to illustrate the position of the silicon PMs. And you can see that we have these light cones different for every channel. So by combining this data, we can also have, especially if we have several scintillator hits, some direction reconstruction inside the radiation monitor, not only between a spacecraft. So this is it. These are my highlights. Just to recap, we evaluated the radiation monitor with simulation experiments. We have validated experimental data with the simulations. And we have seen that we can use this data to have a reconstruction of the spectrum with cosmic rays and SEPs with good enough results. And also, we have assessed, we are underway of assessing the reconstruction capabilities of the directions. And an extra thing that I wanted to say, but I didn't have much time to add, is that we have already built another prototype that we call Hector. It's a reduced version of the final radiation monitor, which is cube-sized sites. And it will be a demonstrator that will be flying along other science diagnostic subsystem instrumentation by the end of the year in a low Earth orbit. So we will have extra data on the performance on flight. And this is it. Thank you very much.
Okay. Do you have questions for Marina? Yes.
Hi, thank you for the talk. So for the baking fiber, we had to space qualify it in terms of both proton radiation as well as gamma ray radiation, right? So I see that you subject your radiation monitor to proton radiation. Is this also planned that you also calibrate it with gamma radiation?
No, but I have an extra slide for you. The radiation monitor is, because we are using plastic scintillators and it was not designed for gamma ray, it's mainly transparent. But if we have a powerful enough gamma ray burst, we can potentially be able to detect this. Because we have the tungsten absorbers in the middle, so we rely on the fact that there are secondary particles that are generated by the gamma rays within the tungsten, and that could also give us a signal. But it's only for very high, very powerful fluxes.
So then, is my understanding correct that the proton radiation is the one that we should pay more attention to, as opposed to gamma ray for LISA?
Yes.
Okay.
Yes, because the protons are the most abundant and are the ones that generate more secondary particles. The gammas are more the spacecraft are more transparent to gammas, so it's more a problem. Let's say the particles.
Okay. Is there anything online? Then I think we can thank Marina and Joseph Hart. Please come up. Oh, sorry. No, wait. There's a question. Let's do it. Do you want to?
The question is there any possibility to have a count rate down to 4 seconds?
Yes. So with the current electronics, we can have, assuming that I understood correctly the question, we can have rates and we can count in beans up until more or less the second. So every second we can have the counts for every channel. This gives us the time resolution. I'm not sure that this was the actual question or not. Okay. But in case, since we are very separated, it's enough time resolution also to have the arrival time at different spacecraft. Thank you.
Thanks. Good. Yeah, so we have Joseph Hart. Please go ahead.
Thanks. So my name is Joe Hart. I'm a laser engineer at the NASA Goddard Space Flight Center. I'm thrilled to be here today to be able to share with you the work done by our excellent team that we've been doing over the last few years to evaluate the performance of the EDU-1 laser system for LISA. Now, if you were lucky enough to attend the NASA tour yesterday, you might have seen us working in the clean room on the EDU-2 laser system. And if you're interested in learning about how this technology development happens, I encourage you to visit Kenji Namada's poster later this afternoon. If you also have any other questions about anything to do with the laser system, you can probably ask him there. But here, of course, since that laser head is not built yet, I'll have to tell you about the laser head we built a couple of years ago and have been testing since then. So I'll start by telling you a little bit about what the laser system is and how it works. I'll then touch on each of the individual subsystems of the laser system and give you some idea of where they stand in their technology development. And then I'll conclude with the bulk of, or the meat of the talk, which is how they test when you stick them all together, maybe put them in a vacuum chamber. So the task we've been given is how do you make a 2-watt laser system that has high frequency stability, high intensity stability, and that you can apply phase modulation to. In order to apply phase modulation, that's relatively straightforward. You buy a phase modulator. One problem is that phase modulators can't take all that much optical power, certainly not 2 watts. So we have a power amplifier that we put at the output of that. Great. Okay, what about the high frequency and intensity stability? You can't just go buy one of these off the shelf. And in fact, they didn't exist at all, at least one that was spaceflight compatible at the beginning of the LISA mission when this was founded. So what do? You get together the best minds at NASA and in industry, and you come up with something and you develop it. And if you want to learn more about the development of the main oscillator, I encourage you to visit Will's poster this afternoon. Of course, once you develop a state-of-the-art main oscillator for LISA, you start to understand, of course, that with LISA, nothing is ever good enough. We need probably 5 orders of magnitude better than that. So what do? You do feedback loops, right? So we continuously monitor the frequency and the intensity of the laser. We feed it back. We feedback so we can monitor those drifts, and we feedback to cancel them out so that we can get ultra-high stability and frequency and the intensity. Of course, all of this system is a fiber-coupled laser system, and if you want to learn more about how optical fibers work in space, what you can do with them, I encourage you to visit Haley's poster this afternoon. So I'll talk a little bit about the frequency suppression loop. As Ryan mentioned in his performance talk the other day, laser frequency noise obscures gravitational wave signal. So we have to suppress it. We can suppress it using a standard technique called Pound-Trevor-Hall locking. We do that by locking the laser to an ultra-stable reference cavity, which we call this the frequency reference system. So what you can see here in blue on the figure is the free-running frequency noise of our NPROs, which I said are state-of-the-art. And we need to suppress it by, like I said, 4 or 5 or 6 orders of magnitude. So that's kind of the task that we are tasked with. Similarly, for the laser intensity noise, we put a power monitor as close as possible on the optical bench to the test mass so we can monitor the laser intensity delivered to the test mass. And we can stabilize that with a feedback loop by feeding back to the power amplifier laser diodes. And similarly, as you can see, the free-running non-stabilized relative intensity noise is about 4 orders of magnitude higher than what we need for LISA. So these control loops have to do a lot of work. There's one more really complicated and difficult measurement we have to make, which I don't have time to describe today. Suffice to say that it is so thermally sensitive that we have to stick it inside a Yeti cooler, or all of the measurement apparatus actually inside a Yeti cooler, so we had to empty out Kenji's refrigerator. Okay, so now that you know how to do this, and we have all the individual components, but we need to know, is it gonna work, right? We're gonna send it very far away, we can't go back and fix it, so is it gonna work? Is it gonna work for 5 or 10 or 15 years? And the only way to know this, if it's going to work and how well it's going to work, is we have to perform performance testing. So we hook up all the individual components, we stick them in a thermal vacuum environment, and we evaluate how they do once you stick them together. First, I want to touch on just briefly the status of the laser system components. So that's, again, the laser head, the laser optical module, the laser electronics module. And I encourage you, if you're interested in this, to learn more about it, to visit Zhaojian's poster this afternoon. But I just wanted to kind of show you some pictures here. So you can see the NPRO, you can see the TRL6 PA unit. These are currently being developed further to make them more space ready. You can see the TRL4 LOM, which was a previous version that's been tested by both NASA and CSEM, and the EDU1 LOM, which is the one that I'll be talking to you about today. The EDU2 LOM is currently being built. And then there's the TRL5 LEM. In this case, TRL5 means that is not vacuum compatible. So when we do the system level testing, the LOM will be inside the vacuum chamber and the LEM will be just outside. The second major component is the frequency reference system. This is heritage from Grace Follow-On. It's built by BAE, but we have made some minor changes, so we need to kind of requalify some parts of it for spaceflight. And you can see that the FRSO has an optical cavity inside of this thermally protective can. If you want to learn more, and so I'll be telling to you about that FRSO. There is a couple of FRSEs. These are totally new and not inherited from Grace. And so we have to fully qualify those as well. If you want to learn more about the frequency reference system, Jen from BAE will be here this afternoon in the poster session. Finally, we have the power monitor. The power monitor that I'll be speaking about today is the TRL5, or non-vacuum compatible power monitor, which you can see in the picture here. We actually have also received earlier this spring the vacuum compatible TRL6 version, which Kylan has been working incredibly hard this week while also attending this conference to get ready. We're starting TVAC testing as soon as tomorrow on that unit. And so we'll be sharing those results with you maybe at the next symposium, but he can talk to you more about it at his poster this afternoon. So now that we know kind of where we're at with the individual components and have some feel for what they look like, and you know who to visit later today, I can tell you a little bit about what happens when we stick them together. So first, I'll talk about what happens when we put the LOM and the LEM together. That's the laser optics, but along with the laser electronics. So what we do in order to make sure that we can test them, make sure that they'll work and test them in a similar environment to what they'll see on LISA, is we do some shock and vibration testing, and then we put them in a vacuum chamber, or at least in this case the LOM, and we temperature cycle them. At each temperature plateau, we execute over 20 performance tests. Of course, I can't tell you all about most of those today. But I will, as I mentioned earlier, kind of the key requirements, or some of the hardest ones anyway, are the frequency noise, the relative intensity noise, the phase modulation, the RF modulation phase noise. But some of the important outcomes of this TVAC test before I get to the data is that the LOM is meeting all of the challenging LISA requirements. I'll prove that to you in a moment. Once we made minor modifications to a couple of LEM circuits. We've also learned that the RIN suppression can couple to the phase noise, and so those we have to be a little bit careful and monitor that going forward. So here are some of the key performance figures from the EDU LOM thermal vacuum testing, and so the different colors here represent those different thermal plateaus, and those are representative of the environment we expect for flight. So you can see that the sideband phase noise, the LOM and the LEM together, are able to meet the very difficult LISA requirement over the entire LISA band. And similarly, the free running frequency noise, which again is only 4 or 5 orders of magnitude too bad for LISA, we're able to meet all of those requirements before we put the FRS inside the system. So now the same test setup, right? The LOM is still inside the TVAC chamber. The LEM is outside. We add the PMON, which is non-vacuum compatible, so that's outside, but as you can see, it's inside kind of a thermally secure environment. And this is really not a great place for the PMON to be. It's not that thermally secure. Vacuum would be much better. Kylan did a lot of work putting it on a zero-dir bench, but it's optically very far away from the laser head. There's very many splices and other components because, as I mentioned, we're doing 20 some odd other tests at the same time. Nevertheless, we were able to actually meet the LISA requirement over the entire band, as you can see in blue here. And at the low frequency band, which is where, in the Lea band, which is most important and also where the Piemont loop, stabilization loop really shines, we're about an order of magnitude better than we need to be. As I mentioned, we needed a slight LEM modification to meet all of these requirements, and that's what's shown in red there. Once we kind of changed the resistor, the oscillation went away, and we were able to meet all of the requirements. And as I mentioned, the next Piemont test is starting today-ish. Finally, we have the frequency reference system. To test this in a space-like environment with temperature cycling is extremely challenging. The frequency reference system is designed to be as thermally isolated, have the cavity be as thermally isolated from the base plate as humanly possible, and BAE works extremely hard to do this, and they do an excellent job. Therefore, as you can kind of see on the plot on the bottom right, the green line there is the base plate temperature, so I kind of stepped that about 5 degrees Celsius, and it takes something like a week for the cavity to equilibrate. So you want to do that thermal vac cycling I was talking about before, and you're looking at 2 months minimum. However, you can learn some really cool things from this incredibly challenging test. You can measure the coefficient of thermal expansion of the cavity itself versus temperature. You can measure the cavity thermal transfer function from the base plate to the cavity itself by monitoring the thermistors. And that allows us to not only verify our thermal model, but it actually helped us to interface with ESA and understand what should be the spacecraft thermal interface requirement. Finally, this test was additionally productive because it allowed us to discover an unwanted etalon inside the original FRSO, and that has informed process changes in the build so that future models won't exhibit this. So these are the results from sticking the FRS inside. Oh, sorry. The first result is from with the laser, the LOM still inside the TVAC chamber and the FRS on top of the tabletop. So here we're not in a great environment for the FRS, but you can see that the frequency reference system is really able to suppress greatly from the free running laser frequency, which is shown in that dashed dot line, to below the Lea requirement almost everywhere except at low frequencies. The reason we're bad at low frequencies is because the room environment is really bad, incredibly bad actually. And so once we put the FRS inside, the FRS itself inside the TVAC chamber to isolate it from the room, you can see the results in the bottom figure there, and we meet the Lea requirement everywhere in the Lea band. I'm running out of time here, so I'll point you to Jen's poster to talk more about the FRSE. Suffice it to say that we have tested the FRSE inside the TVAC chamber, and we find that in the Lea band it is able to meet the Lea requirements, though we still have a little bit of work to do outside the Lea band at tens of kilohertz range. So with that, I'd like to thank you for your attention and just point out quickly that we've been testing the Lea laser system components individually and together, and all the results look promising so far. I encourage you to visit the Lea laser team posters this afternoon to learn more or to ask any questions you might have.
Do we have a question or two? Hey, Paul, can you meet me in the middle? I'm coming.
Hi. You said you couldn't put 2 watts through the EOM. Is there a fundamental reason why not? And would it be helpful if you could?
So I think in order to get a low VPI, you want to keep everything, which is to say you don't need to drive it with too much voltage. You need to keep everything tight optically, and so when you keep it tight, then there becomes a limit on how much power before you eat up your modulator. They also actually age the more power you put through them, and we need ours to last a really long time. It would be helpful, yeah.
Okay. Are there any online questions? Nope. Okay. Thanks. And our last speaker of the session, Francesca Barbieri, please go ahead.
Can you guys hear me? All right. So thank you guys for staying until the end of the session. My name is Francesca. I am a PhD candidate at the Precision Space Systems Laboratory at the University of Florida. And today I'll share some of the results of our environmental testing of the Lea charge management device. Before we do that, however, let's start with why we need charge management in the first place. So we all know Lea will use test masses as the main reference for gravitational waves measurements. We want to keep these test masses in an extremely quiet environment, which means we want to minimize all sort of noise sources. One of these is, for example, the acceleration noise, which we want to keep below 3 femtometer per second square per root hertz at a frequency of 0.1 millihertz. When in space, however, the test masses are going to be subject to charge accumulation due to cosmic rays and solar energetic particles, which can then lead to electrostatic force noise. In LISA Pathfinder, for example, we measure typical charge rates of around 25 charges per second, or 10 millivolts per day. And if left unaddressed, these can limit the LISA sensitivity in the low frequency, hence the need for a charge management system. We also, however, want to keep the near-perfect free-fall environment of our test masses, so we can't just add a grounding wire to discharge them, and we instead need a contactless charge control. So how do we do this? We do this by using the photoelectric effect, so by shining UV light at 250 nanometers onto the test mass or electrohousing surfaces to release photoelectrons and keep the test mass charge within plus or minus 2.4 picocoulomb, which is the requirement for LISA. The charge management system, like many other of the systems in LISA, will rely heavily on LISA Pathfinder heritage, with a key difference, which is that rather than using mercury lamps, we will use ultraviolet light-emitting diodes, or UV LEDs. The UV LEDs have a number of advantages over the mercury lamps. They're smaller, they're lighter, they have higher efficiency, they have a wider dynamic range, but most importantly, perhaps, they also allow us to perform charge control in a new way, which we refer to as the pulse mode. So taking a tiny step back, charge control on LISA will be able to be performed either intermittently or continuously. Intermittent charge control consists in letting the test mass charge up to a predefined threshold and then discharging it all at once using relatively high UV power levels, while continuous, as the name suggests, consists in continuously shining UV light into the sensor, such that the test mass charge can be kept around 0 at all times, and this requires lower UV power levels. Now, both the intermittent and continuous charge control methods can be performed with this new pulse mode, which, as I said, is made possible by the use of UV LEDs. And looking at the graph on the right, we can see that the pulse mode consists in pulsing the UV light, so looking at the red line, in pulsing the UV light with respect to the 98 kilohertz injection signal, which is in gray in the plot on the right. So the pulse mode allows us to cover a wide range of discharge settings by modulating a set of parameters, such as the number of pulses per second, the duty cycle, the drive current, and the phase. The continuous pulse mode is probably going to be the go-to discharge mode for LISA. However, we will also have DC mode, which is the constant light output in the blue line on the graph, based on Pathfinder heritage, which can be used as a backup discharging mode. Now we talked about why we need a charge management, we talked about how we can do charge management, now this is the what, so the hardware that we will use for charge management. The charge management system comprises of a number of parts, two of which are the UV light unit, or ULU, and the fiber optic harness, or FOH. If we take the ULU and FOH together, we refer to this as a charge management device, or CMD, which is what our lab at UF works on. So on the right, we have the ULU with a main and redundant side, 6 LEDs on each side, which are then connected through the fiber optic harness, which routes the light from the ULU into the GRS. At UF, we were tasked by NASA with the design, manufacture, and testing of the CMD for TRL6, Technology Readiness Level 6, for which we want to demonstrate the performance of the system in the relevant environment. So for us, this meant radiation testing of the UV LEDs, electromagnetic interference and electromagnetic testing, compatibility testing, vibration testing, and thermovacuum testing. And today, I will mostly cover the results of the thermovacuum testing campaign of the UV light unit, specifically focusing on this new pulse mode that we can achieve with the UV LEDs. So going over the graph on the right, here we have a temperature profile where we expose the ULU to the non-operating temperatures of -30 and +60 degrees Celsius, followed by 2 survival checks at -20 and +40. And then we characterize the full performance spectrum of the ULU over the 0 to 40 degrees Celsius temperature range. Now, diving into results and starting with the dynamic power range, we have two requirements here that we want to meet. Starting with the plot on the left, we want to be able to achieve UV power levels down to 10 picowatts. So here we have the black line indicating the requirement. We have the LED yielding the highest power output in blue and the one yielding the lowest power output in red, with the gray traces in between representing the other LEDs, such that we have some sort of a performance envelope. And you can see that all 12 of the traces cross that black line, meaning that we are compliant with this low power requirement. On the other side, instead, we have the high power requirement. In this case, we want to be able to get UV power values up to 125 nanowatts. And you can see on the plot that only 3 out of the 12 LEDs that we tested do cross the line, meaning that we're only partially compliant with this requirement. This issue is currently being addressed in the next phase of development, and we will address this by improving the optical coupling such that all LEDs will be able to reach this 125 nanowatts requirement. Now moving on to the power temperature dependence. To look at this, to characterize this dependence, we take the data obtained from high power tests and we extrapolate it at the maximum number of pulses per second that we can drive the LEDs at, which is 98,304. This extrapolated data is then linearly fit over temperature and normalized over the linear fit value at 10 Celsius, which is how we obtain the plot on the right. So on the x-axis, we have temperature. On the y-axis, we have normalized power and the 12 LED traces, where you can see that for all of them, we observe a decrease in power output as temperature increases. Specifically, we measured this relative temperature coefficient to be between minus 0.20% to minus 0.53% per degree Celsius. Now moving on to stability, of course we want to use the charge management to limit the electrostatic force noise. At the same time, we don't want to introduce excess noise. So we have two requirements to make sure that we don't do this. Starting on the left with the relative power stability, we want to make sure that our noise is below 0.1 per root hertz. So here again, we have the black line indicating the requirement. We have the blue and red indicating the maximum and minimum noise measured at each frequency respectively, and then the gray traces in between representing the LEDs. So here, all of our traces are below the black line, meaning that we're meeting this requirement. And similarly, on the right, we have the relative phase stability. In this case, we want our phase noise to be below 7 milliradian per root hertz. And again, we see all traces below the black line, so we're meeting both the relative power and phase stability, and we can make sure that our charge management system does not add excess noise into the GRS. Now, one last result I'll be showing today is about the spectral emission profile. We want to make sure that we have consistent photo emission across the LEDs such that we have reliable and predictable charge control. And we do this by looking at two main requirements. One is that the peak wavelength of all of the LEDs shall lie between a wavelength band between 247 and 259 nanometers. And the second is that at most 10% of the spectral emission profiles can fall outside a reference envelope. So looking at the plot on the right, we can see that the peak wavelength of all 12 LEDs does in fact lie between this wavelength band that I specified earlier. So we're meeting the first requirement. And we then calculated that the maximum out-of-envelope fraction of the LED across all temperatures and across all 12 of the LEDs was 5.4%, so below the 10% requirement, meaning that we are meeting these requirements as well. Now, with the ULO performance verified in the relevant environment, we started working on to the next development phase, which is the Engineering Testing Unit, or ETU. We are currently working on improving the optical coupling to address the partial compliance with the high power requirement, and we're also working on improving the testing setup for the next thermal vacuum campaign. Once ETU is completed, we will be moving on to flight phase, during which we will develop and test 6 flight units plus spares that will then be delivered to ESA for integration with the spacecraft. And while I'm here, I wanted to mention a few of the related work that we have at the symposium. We have 4 posters from other members of our lab. One on the LTPDA toolbox, one on the ULO magnetic testing. We have a poster on simulating photoelectric charge management in the GRS, and one on the impact of SEP's events on the charge management system performance. We also have 2 papers out that you can find by scanning the QR code on the slide. One is on what I presented today, so LISA charge management device design and performance, and the other one is on simulating the UV light propagation through the FOH. And that is all from me. Thank you.
Okay, we're going to start with an online question. How was the radiation testing of the UV LEDs done? Protons, gammas, etc.?
That is a great question. I'm not entirely sure. This information is on the paper, and there is a chance that a specific paper on radiation testing will come out eventually.
Okay, so look to that. Do we have any other questions? Yeah, okay, maybe related.
So regarding the spread in the spectrum of these LEDs, right? So I was wondering if you can elaborate a bit more on that. Is it by construction, or is it related to the temperature environment, or, I mean?
So the reference envelope you see here in the green shaded region is basically, imagine we have one spectrum on the left side and one spectrum on the right, and then we combine the peak of both. And that reference is based off of 2 specific type of UV LEDs that were studied, and I believe that might have been the right wavelength that we know the properties of when it comes to charge control and discharging with the photoelectric effect.
Thank you.
Okay, all right, I'm coming, Kenji. Oops, there's a chair there. Okay.
Hello. What is the phase noise here? Is it optical or timing, and why do you care?
Can you repeat, sorry?
Yes, well, could you define better the phase noise that you're referring to and why it's relevant?
Yes. So for the phase noise, we have this relation between the phase and the test mass voltage, which is that the voltage changed by 0.6 volts per radian. So we want to make sure that we maintain the LED phase stable enough such that we're not introducing a noisy charge onto the test mass. So we have a certain allocation for the noise that can be introduced, I guess, by the charge management system when we operate, and these 2 specific requirements are derived such that we are below that threshold.
Okay, so thank you. We should thank all of our speakers. And there's the poster sessions.